In the coming few lectures, we will learn about approximate counting. So, we can look at the problem in the following way. There is a set S, okay, and its description is given in some particular way, and we need to know how many elements are there in this set S. Now, the presentation of S is extremely important. How exactly is S given, and that is going to have bearings on the computational cost associated with this counting. Let us look at a couple of examples of such counting problems. One, given a Boolean formula phi, let S be the set of assignments satisfying phi. Okay, so, we need to count the number of satisfying assignments for a formula. Another kind of counting problem could be given a graph G equals B comma E, let S be the set of spanning trees of G. A third example could be given a bipartite graph let S be the set of perfect matchings in, so let us say if we call this bipartite graph G, we want to know the number of perfect matchings that are there in G. So, if you think of each of these as computational problems, in the first case the input is a Boolean formula of a certain length, and in the second case it is a graph of a certain size, and in the third case it is a bipartite graph of a certain size. And our answers depend on the formula and the graphs that are given as input. But how large can these answers be? For a Boolean formula, let us say n variables, the answer, the count could be as large as let us say 2 to the power n. And given a graph, the set of spanning trees also could be exponential in the number of vertices, and same for perfect matching. Okay. But these are numbers, and therefore, they can be output by some string of length log exp n. Okay. In the sense, the output is going to be polynomially long in all these three cases. When the count is extremely large, that is, it is prohibitively large to even display it, I mean that is not a problem within our computational abilities. But see, all these problems are the characteristic that the answer, the final answer is not too large, it is polynomially long in the input size. Contrast this with the case where we had to list the set of all satisfying assignments. That would have been a very difficult task, because there could be as large as 2 to the n satisfying assignments, and there could be exponentially many spanning trees, and there could be exponentially many perfect matchings. A related problem would be to sample uniformly from these exponentially large sets. So, the set S as such could be exponentially large. If we were able to count it, that is an interesting thing in many cases, and sometimes we are more ambitious, we want to list the set of elements in S, but that could be troublesome because the set could be very large. In that case, we might reduce our ambition and say that we want to uniformly sample elements of S, and there are some interesting relationship between sampling and counting. So, now let us look at these problems a little more formally. what are the questions that we will be addressing and what are the requirements on the quality of our answers. So, let us look at one class of computational problems called as decision problems. So, these are computational problems with, so we will just informally write it as with 0 1 answers. Okay. So, examples would be, is there a Hamiltonian cycle in G? Another example would be, is there an Eulerian cycle in G? So, G is the input. A third example would have been, does the given system of linear constraints have a feasible solution with variables taking integral values? Another example of a decision problem would be, is there a perfect matching in a given bipartite graph? These are all problems known as decision problems, and some of these decision problems has nice algorithms, and some of them are known to be a little more difficult to solve. So, we could say that a certain decision problem belongs to the class P or polynomial time if we could answer the decision problem. Okay. So, in polynomial time, so the decision problem can be answered in poly time. So, in particular, if you look at say Eulerian cycle problem, the input is an arbitrary graph and we want to check if it contains an Eulerian cycle. There is an algorithm which will answer this question for every graph, and the algorithm's running time is bounded by a polynomial in the input size. Therefore, we will say that this problem, Eulerian cycle problem, belongs to the class called as P or polynomial time. Now, we could ask this with associated with each decision problem, we could also construct a related counting problem. How many Eulerian cycles are present in this particular graph? That is a more complicated question. Now, note that if we could solve the counting problem, we will always solve the decision problem, because the counting problem, if the answer to the counting problem is greater than or equal to 1, then we know that the decision problem's answer is yes. So, counting problems, one should expect that the computational cost associated with the counting problem is more than that of the decision problem. Let us look at another complexity class called as NP. This is called as non-deterministic polynomial time. So, look at all decision problems for which you can have a non-deterministic polynomial time algorithm. That will essentially be called as the class NP. Let us take an example. Is a given number composite? So, the input is let us say n digit number denoted by capital N, we want to know whether this is a composite number. Now, the non-deterministic polynomial time algorithm to do that would be guess a factor, check that the factor divides n. So, the input is n. Okay. If the factor divides n, you will say it is composite, otherwise you will say not composite. Now, this algorithm has the feature that for any composite number, there is a correct guess that will cause the algorithm to say yes, the number is composite, and for every prime number, there is no guess which would force the algorithm to say that the number is composite. Of course, for composite numbers there are wrong guesses, that is true, but for every composite number there is at least one right guess, and therefore, we will call that this problem or this decision problem composite versus non-composite, that is in NP. There is of course the polynomial time AKS algorithm, which checks whether the number is composite or not, and it does not involve any guessing. Similar question would be, is there a Hamiltonian cycle in G? Again, you can have a non-deterministic polynomial time algorithm, that is an algorithm which will make a guess and verify using that guess that the graph contains a Hamiltonian cycle, and the entire computation gets done in polynomial time. So, now why are we looking at P and NP? When we look at the various counting problems that we are faced with, we could imagine that there is an underlying sample space, a large sample space, say which we call U, and this is split into two parts, the set which has the required property and the complement set. So, for each element we could check whether the particular element, I mean let us say you take one element and check whether it belongs to S or it belongs to S complement. You do this for every element in the universe, you will get a count. Well, that is not an efficient algorithm if U is very large, but this question itself, does the sampled element or the arbitrarily picked element have the particular property or not, that we can view as a decision problem. That decision problem may have a polynomial time algorithm, or in some cases it might have non-deterministic polynomial time algorithm. The class of problems that we are interested in for counting is those problems whose decision problems have a non-deterministic polynomial time algorithm. They should have at least a non-deterministic polynomial time algorithm. Naturally, this class P is completely contained inside NP. Okay. So, now let us look at some more concrete example. Let us look at this problem. The input is a graph and the output we want to be the number of spanning trees of G. Clearly, does G have a spanning tree? This question can be answered in polynomial time. Okay, if it is connected, we can say that it contains a spanning tree, or if we just assume that the input graph is connected, we know that trivially it is going to have a spanning tree. So, the decision problem associated with it is a very simple problem, it can be solved trivially in polynomial time, but what about the counting problem? Can we estimate or can we find out the number of spanning trees in a given graph? For example, if we had taken this particular graph, it is a simple graph. So, this is 4 vertices and 5 edges. How many spanning trees does this have? Well, if you keep the edge 1, 3 in the spanning tree, then so let us look at the number of spanning trees for this particular graph. This could be 1 and there are 4 such. And these are the ones without the diagonal. If the diagonal is there, then this is 1, this is another, okay. So, there are 4 such as well. So, in total there are 8 spanning trees. So, here we had enumerated them and one can verify that there are no more. So, it looks like some kind of I mean you will have to try many possibilities and check if it is a spanning tree and so on. There is a theorem called Kirchhoff's tree theorem, which basically helps us solve this problem quickly. So, the theorem says, suppose you look at the matrix A, which is the adjacency matrix for the graph. Okay, so, A let us call it as the so in this case it would be the matrix with 1, 2, 3, 4. Two 1 is an edge, 2 0 is not an edge, 2 3 is an edge, this is not an edge. 4 1 is an edge, 4 3 is an edge, the others are not an edge. This is the matrix A, and we can have a diagonal matrix which lists the degree of each vertex. So, 1 is of vertex degree 3 and the others are of 2 is of degree 2, 3 is of degree 3 and 4 is of degree 2 and everything else 0. So, if you look at the matrix D minus A, that is going to be the following matrix with 3 2 3 2 on the diagonal, they were 0 and the other entries are all negative. Okay. So, this matrix D minus A in general is going to be, for any undirected graph, this is going to be a matrix whose determinant is 0, because if you add up any row, for that matter any column, the symmetric, you will get 0, because for each edge there is a -1 and you have the degree on the diagonal. So, if you add up any row, you will get 0. So, the determinant of this is going to be 0, but you can just remove a row and a column, okay, and then try and evaluate the determinant, and that determinant would be called as a minor. So, look at a minor of D minus A and look at its determinant, that will be equal to number of spanning trees. Okay. So, this is Kirchhoff's tree theorem, and because of the tree theorem we can compute all these quantities. Determinant computation can also be done in polynomial time, and therefore, this problem of computing the number of spanning tree can be done in polynomial time. So, this is an example where the decision problem is also polynomial time and the associated counting problem is also polynomial time, even though the total number could have been exponentially large. If you take the complete graph, it will have n raised to n minus 2 spanning trees. So, it is a large number, but still that computation could have been done in linear time. If we had, let us say, taken each spanning tree and checked whether it is a spanning tree, then we will have to do large number of computations. We do not have to do it because of Kirchhoff's tree theorem. Now, let us look at another problem called as perfect counting the number of perfect matchings. Okay. So, we will look at a bipartite graph and the number of vertices on either sides will be equal, because otherwise there will not be a perfect matching. We want every vertex to be matched to some other vertex. So, let us say this is 1, 2, 3, 4, 5, this is 1, 2, 3, 4, 5. We can call them as A1, A2, A3, A4, A5 and B1, B2, B3, B5. So, again the question of existence, does there exist a perfect matching? This can be solved in polynomial time, because it can be converted into a network flow problem. It can be solved in many other ways. So, this question can be solved in polynomial time, but we want to know how many are there, and that becomes a more complicated problem. Okay, what is known as the following. So, let us say we can again construct a matrix corresponding to it. Okay, so, we will have vertices 1, 2, 3, 4, 5 on the columns, on the rows. This is corresponding to the side A, and for the other side we will have it on the columns. Okay. 1, 1 as an edge, so you put a 1, 2, 1 as an edge, so you put a 1 and so on. Okay. So, this is some kind of adjacency matrix for the bipartite graph. You can think of it as a reduced adjacency matrix, because ideally there would have been 2n vertices, okay, but because it is bipartite, let us say this were A, this is B, this is B, this is A and this is B. A to A there are no edges, so this will be 0, B to B there will be no edges, and since we are looking at an undirected bipartite graph, we can say that these parts will be symmetric. So, we are just looking at this part. Looked at two problems, one is the spanning tree and the other is bipartite matching. The count, the number of spanning trees and the number of perfect matchings, although both the decision problems of polynomial time, we saw that one can be easily computed, but the other we do not readily have an algorithm to do those computations in polynomial time. We could also look at problems which are in NP. For example, we could look at a general Boolean formula and we want to compute the number of satisfying assignments. If we could do this for arbitrary Boolean formulas, depending on whether that number is 0 or 1, we would have solved the decision problem for SAT, and SAT being an NP complete problem, we could have concluded that P equal, if there was an algorithm to count the number of satisfying assignments for an arbitrary formula, we could have easily solved P versus NP problem. So, this one should expect that this is going to be difficult, but what about suitable restrictions? If we restrict these Boolean formulas to certain kind of formulas. So, the kind we are interested in is what is called as disjunctive normal form. Okay, so, let us describe what is disjunctive normal form. So, our formula phi is of the form C1 or C2 or C3 or Ck, where each Ci is of the form L1 and L2 and L3 and Lk, where each Li, okay, let us call this C, Li11, Li22, Li3 or Li1, Li2 and Liki. okay, where each Li known as a literal is either let us say x alpha or not x alpha. It is either a variable or the negation of the variable, and we may assume that each clause contains at most one occurrence of a variable, because if two occurrences of the same variable appears, if they are in the same format, we can just replace it by a single one, or if they are of opposite kinds, we can say that that particular clause is unsatisfiable, and therefore, the formula can be simplified further. So, we are given a formula of this kind, okay, and we are asked the question, how many satisfying assignments does this particular formula have? For example, if we have taken phi is equal to x 1 or x 2, sorry, x 1 and x 2, or not x 1 and x 2, or x 1 and not x 3. Okay. So, there are 8 possible assignments. It is clear that by checking just the first clause itself, we can find an assignment which satisfies them, satisfies all of them. Okay. For example, x 1 equals 1, x 2 equals 1 and x 3 equals 0 would satisfy the first clause, and therefore, it would satisfy the entire formula. But there are other things as well. X 1 equals 1, x 2 equals 1, x 3 equals 1 is another one. So, we can just look at all possible 8 assignments and describe the total number, but that is an exponential time algorithm. So, these are the typical kind of problems that we are going to look at when we study counting. When we talk about approximate counting, that arises because the exact counting may be difficult in many cases. In case of spanning tree, we could get the exact count by a polynomial time algorithm because of Kirchhoff's tree theorem. In case of perfect matching, we can think of the problem as computing the permanent of a matrix, but computing permanent is known to be difficult. So, we cannot hope to find the exact values. In case of satisfying assignments for a Boolean formula, again, if we could compute it exactly, then we would have solved the P versus NP problem. So, therefore, we will be less ambitious and say that instead of computing the exact value, can we get the approximate answer? Okay. That is the general theme of approximate counting. And we will in addition allow randomization. Okay. In the sense, our approximate counting needs to be correct only with a certain probability. Okay. We will mix two themes. The formal definitions for that we will see in the next lecture.